All right, so this problem says express the displacement current in a capacitor in terms of the capacitance and the rate of change of voltage. Okay, so let me show you what the displacement current is first. Here are the Maxwell's equations. Again, these are the causes, and here on the left-hand side are the effects. Okay, so this equation says this is current density producing magnetic fields. Okay? And you might recall that current like that will produce magnetic fields like so. Okay? Now, what is this term? The second term. This is time-varying electric fields producing magnetic fields. Okay? And you see, if you look at this term, that term is exactly like that. And this guy is called the displacement current density. Okay, so time-varying electric fields are behaving like currents. Okay, so that's what that is. So the displacement current density is epsilon naught delta E by delta T. So this is behaving like a current. Okay. And so that's what they're asking over there. So the displacement current density is epsilon naught del E by del T. Okay. And now here's where this comes in. So as you're charging a capacitor, you close the switch and current flows in there and charges the capacitor. As the capacitor is charging, this electric field between the capacitance plates is increasing. Yeah. All right, for a capacitor, the capacitance is given by Q over V. V is Q over C, okay, the voltage. And the voltage is the electric field times the distance between the plates. Okay. So that's equal to Q over C. And for a parallel plate capacitor, that is E A over D. Okay. So we're going to use this and plug it in there. So the displacement current is J, and now I'm not going to write down the vector notation times the area. Okay, so it's equal to epsilon naught del by del T E times area. So displacement current is epsilon naught A. E is and actually so voltage is E times D. Okay, so from this equation, E is voltage divided by D. Del by del T of voltage divided by D. And this fellow right here is the capacitance. Okay. So the displacement current is the capacitance times del V by del T. Okay, this term is behaving like a current. Okay, so just like this current produced a real current produced a magnetic field like that. So when you're charging a capacitor, let's say this is positively charged, this is negatively charged. Okay, this is electric field that's and the voltage is increasing, and this voltage will produce a magnetic field just like this guy in that direction. Okay, So as long as the capacitor is charging, it's producing a magnetic field. Once the capacitor is fully charged, what happens to the magnetic field? It goes to zero. Once this is fully charged, this goes to zero, this displacement current goes to zero, and the magnetic field goes to zero. Okay? So that's what's happening. All right, so here's a similar problem again. This actually shows you the capacitor. Here's a current flowing into the capacitance, and as the charge builds up, the electric field is changing. So the potential difference across this capacitor between the plates shown is instantly increasing at this rate, okay, 10 million volts per second. What is the displacement current between the plates if the separation between the plates is 1 centimeters and the area of the plates is that? Okay, so this is an air-filled capacitor. Again, you just saw that the displacement current, all right, the displacement current we just found is C times del V by del T. C is epsilon naught area by D times del V by del T. Okay. So we'll plug in all those values. The displacement current is epsilon naught is 8.85 times 10 minus 12, and the units are epsilon naught coulomb square, Newton meter square. Area is 0.2 meters square. D is 1 centimeters times del V by del T. Okay, and del V by del T is 10 to the 7 volts per second. Okay. Okay, so the displacement current is, let's do this. So that's 10 to the minus 10 times that's 10 to the minus 3. So it's 8.85 into 0.2 into 10 minus 3 and amperes. Those units will work out into amperes because current is in amperes. All right, so this is 1.8 amps, okay, 1.8 milliamps. So that's the displacement current. Okay? And generally you've seen that capacitors will charge in, depending on the time constants, will charge fairly quickly. And so that's the current while they're charging. That's the order of the current. Milliamps. Okay, in this problem, you have if the electric and magnetic field strengths vary sinusoidally in time at a frequency of 1 gigahertz, being 0 at t equal to 0, then E equal to E naught. So there is the electric field and there is the magnetic field. When are the field strengths next equal to 0? Okay. So they're varying sinusoidally, and the electric field is at t equal to 0, it's 0, and so on. Okay. So here's the electric field, here's the sine function. Okay, the sine function is 0 at 0, and the next time it's 0, it's at pi. Okay, so 2 pi ft is pi. Okay. So 2 pi ft equal to pi. Okay, and so t equal to 1 over 2f. Okay. And 1/2 frequency is gigahertz, 10 to the 9 hertz. Hertz is 1/seconds. So 0.5 into 10 to the minus 9 seconds. Half a nanosecond later. Okay, at t equal to 0.5 nanoseconds. Okay, and so the period is 1 nanosecond. When do they reach their most negative value? They reach their most negative value when 2 pi ft is 3 pi by 2. Yeah. So then reach their most negative value at 2 pi ft equal to 3 by 2 pi. 3. And this was 10 to the 9, 1/second, so 3/4, 10 to the minus 9 seconds. 0.75 nanoseconds. Okay. For one complete cycle, what is the time needed for one complete cycle? Period is 1/f, 1/. So in electromagnetic fields, actually the frequency for visible light, this is a gigahertz. The frequency for visible light is about 10 to the power of 15 hertz. Okay, so things change very fast. Okay, this problem says a radio station broadcasts at a frequency of 760 kilohertz. So this is about 1 megahertz. And FM radio broadcasts at what signal? At what frequency? 100 megahertz. Those are the frequencies. 100, 105. Okay. So this is, I guess this is AM radio. At 100th the frequency. At a receiver some distance from the antenna, the maximum magnetic field strength in the electromagnetic field is detected to be that. Okay, what is the Earth's magnetic field? The Earth's magnetic field is about 10 to the minus 4 Tesla. Okay, so this is a 10 million times weaker than that. But this is an oscillating field. Okay, what is the maximum electric field and what is the wavelength of the electromagnetic wave? All right. So you saw that for an electromagnetic wave, here's the electric field. We'll call this the electric field, and the magnetic field, of course, is perpendicular to goes like that. Okay. All right. So you guys know that. All right. I don't want to. So Emax. Emax is C times Bmax. That's how they're related. Okay. So Emax over Bmax is that. So Emax is C is the speed of light 3 times 10 to the 8 meters per second times 2.15 into 10 to the minus 11 Tesla. Okay. So that is 6.45 into 10 to the minus 3 volts per meter. That's the electric field strength. Okay, and what do you do with that electric field strength? You stick a dipole antenna out and pick up that frequency with the appropriate. So and this will always have a resistance. Okay. So with the variable capacitor, you change the capacitance such that the frequency of this guy matches this frequency, and that electric field will drive a current in this antenna. Okay. What is the wavelength of the electromagnetic wave? Yeah. The wavelength is, of course, C over frequency, 3 times 10 to the 8 meters per second. And the frequency is 760 kilohertz. Hertz is 1 over second, so that cancels and you get meters. So that's points. This is 0.76 times 10 to the 6. So 300 divided by 0.76. Okay. 395 meters. So the wavelength of this frequency is 400 meters, which is roughly from here to Mainland High School. Yeah. All right, this problem says, at what distance does a 100-watt light bulb produce the same intensity as a 75-watt light bulb produces 10 meters away? Okay, intensity is given by the power divided by 4 pi r squared. Okay, so assuming a point source that is emitting equally in all directions, the intensity, that is the energy cost passing per unit area per time, is given by that. All right, so what you want is, let's say that's power 1, 4 pi r1 square. You want that intensity to be the same as that. Okay, so if the power of your source is higher, then you're further away, you get the same intensity. Okay. So R2 square is equal to R1 square divided P2 over P1. R2 is R1 square root of P2 over P1. Okay, so if P2 is 100 watts and that's 75 watts, at this distance, you'd get the same power that P1 gives at that distance. So R2 is, let's say, 10 meters times 100 watts divided by 75 watts. So that works up to 11.5 meters. So at 11.5 meters, from a 100-watt bulb, you get the same intensity that you would get at 10 meters from a 75-watt bulb. Okay, this problem says a small helium neon laser has a power output of 2.5 milliwatts. You know, those old-time red lasers, those are about 5 milliwatts, less than 5 milliwatts. So that's what this was. So what is the electromagnetic energy in a 1 meter length of the beam? Okay, so the power is 2.5 milliwatts. What does the power mean? The energy emitted per unit time, per second. Okay, so let's say you turn on the beam and turn it off for you'll have it lit for 1 second. The length of the beam would be how much?
Speed of light times time?
Which is 1 second.
Mm-hmm.
So which would be C meters. Okay, and how much energy does this guy contain? E is equal to P times T, 2.5 milliwatts times 1 second, 2.5 millijoules. Okay, and so 1 meter of this will contain the energy contained in 1 meter would be the total energy divided by the length, C meters. Okay. So did you guys understand this? I turn this laser on and I want to find the energy in 1 meter of that beam. Okay, so so the energy in 1 meter is 2.5 millijoules divided by 3 times 10 to the 8 meters. Okay. Point 0.83 millijoules per into 10 to the minus 8 millijoules per meter. So that's the amount of energy per meter of the beam. Okay, so or 8.3 into 10 minus 12 joules per meter. That's the energy per meter of that beam. Okay, this problem says at the top of the Earth's atmosphere, the time average pointing vector tells you the intensity of the electromagnetic wave. Yeah. Associated with sunlight has a magnitude of 1.4 kilowatts per meter squared. Okay, so at the top of the atmosphere, the intensity of light is 1400 watts per meter squared. This is a good number to remember. Half of it reaches the surface of the Earth, and the other half is reflected. So 700 watts per meter squared is what reaches the surface of the Earth per meter squared. Okay. That's this meter square. This meter square gets less because it's at an angle. All right. What are the maximum values of the electric and magnetic fields of this intensity? Okay, so if you look up your notes, So the average intensity, which is that, is equal to E max, B max divided by 2 mu naught. Okay. So, and E max and B max are related. So E max is B max times C. So average intensity is C over 2 mu naught B max squared. Okay, so let's find B max. B max. So the amplitude of the magnetic field's strength of the magnetic field here in this electromagnetic wave is given by this. Okay. All right, so let's, so this is square root of 2 mu naught is 4 pi times 10 to the minus 7 Tesla meter amp. The intensity is 1400 watts per meter square. And C is 3 times 10 to the 8 meters per second. All right, let's do the powers of 10 first. That's 3, so that makes it 10 to the 5. That makes it 10 to the minus 12, square root 10 to the minus 6. Okay. So B max is square root of into 10 to the minus 6. And what are the units?
Tesla?
Tesla. All right, let's do 8 pi times 1.4. Okay, so that's 8 pi, and there's 1.4 and 3. All right, so here's why I wrote it like so. So that's roughly the strength of the Earth's magnetic field. So the electromagnetic field has a strength at 10th the Earth's magnetic field. What is the power radiated by the sun, assuming that the Earth is 1.5 times 10 to the 11 meters from the sun? Now, for part B, so here's the sun, and here's the Earth. The intensity is given by the power of the sun divided by 4 pi r square. Power is intensity times 4 pi r square. And intensity was 1400 watts per meter square. 4 pi, and Earth-Sun distance was 1.5 into 10 to the 11 meters squared. Okay. So this is 10 to the 22. We'll make it 10 to the 25, and I'll do it right here. So power is 1.4 into 4 pi into 1.5 square into 10 to the 25 watts. Okay, so roughly 4 times 10 to the 26 watts. And so this is, and now I'll write it like so, 10 to the 24 into 100 watts. So what did we calculate? The power emitted by the sun, okay? That's a 100-watt bulb. So 4 trillion 100-watt bulbs. Okay, that's how bright the sun is. All right, so this problem says a 2.5 meter diameter university. So 2.5 meters is roughly the size of this table. Okay. Diameter university communication satellite dish receives a TV signal that has a maximum electric field strength of 7.5 microvolt per meter. What is the intensity of this wave? So here's the dish. And the intensity of this wave is electric field strength of that. So E max, B max over 2 mu naught. And of course, B max is E max by C, so it's E max square divided by 2 mu naught C. Yep. So intensity is 7.5 into 10 minus 6 volts per meter square divided by 2 mu naught is 4 pi times 10 to the minus 7 Tesla meter amp, and C is 3 times 10 to the 8 meters per second. Okay, intensity, what are the units for intensity?
Watts per meter squared.
Watts per meter square. Okay, that's 10 to the minus 12. That makes it 10 to the minus 5. And 8 is 10 to the minus 13. Okay, and what do we have? 7.5 square, 8 pi into 3. 12 minus 5, yep, minus 13, okay. Okay, 0.75. Okay, so that's the intensity falling on the antenna. Yep. So why do we have dishes? That intensity is too low. What do? You pack, so intensity is power divided by area, and intensity, so power is intensity times area. So you take the larger the dish you have, you can concentrate all that energy on a small antenna there. Okay, and increase the power to the antenna.
That's why antennas have that, you know, those things.
Yep, that's where all the electronics are at the focal point.
Mhm.
So the larger your collection area, larger this area, more power you can deliver to your electronics. Okay, what is the power received by the antennas? Oh, so we are calculating that. So what is the power received by the antenna? The power received by the antenna is intensity times the area of the dish, okay? And it's not this area that's relevant, it's this area, pi r squared, okay? Because that's the area being covered by this beam. So equal to intensity times pi r square, and the intensity was 75 times 10 to the minus 15 watts per meter square. Pi r is, it's a 2.5 meter diameter, so 1.25 meters. Again, that's much power is received by the antenna. Okay. And if the orbiting satellite broadcasts uniformly over an area of this much area, a large fraction of North America, how much power does it radiate? So the intensity reaching the ground is this much, and we'll have to multiply by this area. Okay. So the satellite up in space is radiating power, and it's covering, the area that is being covered is 1.5 times 10 to the 13 meters squared. So the power of the satellite, power is the intensity that's reaching the Earth times the total area of coverage, which is 75 times 10 to the minus 15 watts per meter square times 1.5 into 10 to the 13 meters squared. Not bad. 1 watt. Okay. So of course, so what if you don't want to carry around a big antenna like this in your pockets? Like for instance, satellite phones. So you have to increase this intensity at the ground level. Yeah. That means this power has to increase. Okay. So more sensitive receiver you have nowadays, with GPS and all that, and satellite phones. So you can increase the power of transmission. All right, a microscopic spherical dust particle of radius 2 micrometer and a mass of 10 microgram is moving in outer space at a constant speed of 30 centimeters per second. A wave of light strikes it from the opposite direction of its motion, and it gets absorbed. Assuming the particle decelerates uniformly to zero speed in 1 second, what is the average electric field amplitude in the light? Okay, so here's a beam of light hitting this dust particle that was going at 30 centimeters per second. And what's this beam of light going to do? It's going to stop it in 1 second. Okay. So let's find the acceleration of, there's the acceleration. The acceleration of the dust particle was delta V by T, and its speed changed by 30 centimeters meters in 1 second. So it's 0.3 meters. So the force that was exerted on the dust particle in stopping it was mass times acceleration, 10 microgram, 10 minus 6, and each gram is 10 minus 3 kgs, times the acceleration of 0.3 meters per second squared. So 3 into 10 to the minus 9 newtons. That was the force that was exerted. The force that the beam exerts when it's absorbed is, the force is pressure times area. The pressure exerted is the intensity of the beam divided by C. Okay, so here's the formula. So this is the momentum transferred when you absorb this much energy. The pressure is S, the Poynting vector, divided by C. That's the intensity. Okay, so the average pressure, the pressure is intensity divided by C times the area. Okay. Okay, so what is it that we're trying to find? We find the intensity, and from there, what is the average electric field amplitude? We'll find the intensity, and from there find the electric field amplitude. Okay, so this is a bit involved. So force was intensity times and area is pi r square. It's a spherical particle and the area of cross section is a circle. So the force exerted was 3 times 10 to the minus 9 newtons. C, the speed of light, is 3 times 10 to the 8 meters per second. Pi r, the radius of the particle is 2 micrometer. Oh, yeah, the radius of the particle is 2 micrometer. 2 into 10 minus 6 meters squared. So there is the intensity, and that works out in watts per meter square. All right, this is 10 to the minus 12. That becomes 10 to the 3, 10 to the 11. Okay, so all right, so 9 times 10 to the 11 divided by 4 pi watts per meter square. That looks like a pretty intense beam.
Where'd the 4 pi come from? Should it be 2 pi? Oh, because it's squared. Never mind. I see it.
This is a pretty large intensity. So that intensity will stop the particle in 1 second. Okay. Oh, and then we have to find so the intensity is E max square divided by 2 mu naught times C. And so you can solve for E max from there. Okay, I won't do it. Okay, so just put that in and calculate the electric field strength. Okay. Is this the last problem? Yeah, okay. So what is the frequency of a 193 nanometer ultraviolet radiation used in laser eye surgery? Assuming the accuracy with which this electromagnetic radiation can ablate the cornea is directly proportional to the wavelength. Okay, so why are we using UV light? Okay, do you guys know how eye surgery works? Okay.
They shine lasers in your eyes to fix the receptors?
No, not the receptors. So here's what's going on. So you guys know that light rays, okay, a light ray, when it goes from medium 1 to medium 2, why does it bend?
Because the speed is changing?
The speed is changing, okay? And see, most of your eye is just essentially salt water. Once it goes inside the eye, it can't bend too much because the material doesn't change a whole lot and the speed doesn't change a whole lot. So most of the bending happens when it goes from air into inside your cornea. So most of the bending happens in the cornea, at the cornea. In fact, 75% of the bending happens near the cornea. So 75% of the diffraction or refraction happens at the cornea. And again, why is that? Because it's going from air to salt water. Okay. So when you have a problem, okay, so here's an image, you're trying to form an here's an object, you're trying to form an image there. Okay, most of the bending is happening at the cornea, so that's where you're going to fix it. Okay, so since your eye is not focusing on the retina. And so what they do is, okay, they'll cut the retina, they'll cut the cornea, make an incision there, and fold it back, and then reshape it by ablating cells there. Okay. Go ahead.
No, ablating is a familiar term.
Huh?
Ablating is a familiar term that I've never heard used on an eye before.
Yeah. Oh, well, so what, you do a lot of machining and stuff like that?
No, I was thinking of like rocket
Yeah.
shields.
Okay, yeah, there you go. But that's the idea. Now you're reshaping the cornea by burning off cells. You want to be as precise as possible. Okay, so if you use a light of that wavelength, that is the smallest area you can ablate. That's the smallest dimension you can ablate. So the smaller the wavelength, the sharper your scalpel. That's the idea. Okay. All right, so that's LASIK surgery. All right, so there's the frequency. What is the frequency of the nanometer? Okay, by the way, so the size of a cell is roughly a micrometer. So this is nanometer is 0.193 micrometer. So roughly the wavelength is roughly a tenth the size of a cell. I don't know what the size of the cells are in the cornea, but that's what that means. Yeah. Okay, so frequency of this light is, C is frequency. Uh, 193 into 10 minus 9 meters. So the frequency is, that's 10 to the 17, or what we'll do is we'll do 1.93, 10 to the 15. Hertz. Okay. That's about 1.5. Okay, so that's the frequency of the laser that is used. Assuming the accuracy with which the cornea is directly proportional to the wavelength, how much more accurate can this UV radiation be than the shortest visible wavelength of light? The shortest visible wavelength is 400 nanometers. Lambda blue, so we'll use blue, is 400 nanometers. Okay, so the UV light being used is 193 nanometer. So it's twice as accurate. Okay, so you can cut half the area of light, then blue light. All right, good.